Here are solutions to quiz number 6 for ECE 320 Digital Electronics. This quiz covers H-bridges, DC to DC converters, semiconductor relays, Fourier transforms, and Boolean logic. So the first problem is, given this H-bridge, find the voltages and currents. Well, let's start out with which transistors are turned on, which ones are off. And pretty clearly T1 is turned off because there's no voltage across that diode. And T4 is off. Again, 0 volts to 0 volts, no voltage across this diode. Transistor 2, I've got 10.7 volts across the silicon diode, 9.3 volts at 1K, gives you 9.3 milliamps. If the current gain is 60, that allows 558 milliamps to flow. Transistor 3, I've got 10 minus 0.7, makes that 9.3 volts. 9.3 volts across 1314 ohms gives you 7 milliamps, times beta gives you 424 milliamps, and the most this current can be is 10 volts minus 0.2 minus 0.2, 9.6 volts over 20 ohms gives you 480 milliamps. Now of these three, the smallest one limits the current, and that's this one right here. That tells you that transistor 3 is active. The voltage drop across it is somewhere between 0.2 and 10. Again, on the load line, right here is off, right here is saturated. Anything in the middle is active, so I really don't know what this voltage is. It's somewhere between 0 and 10. Over here, this one's saturated. I know what the answer is. When I saturate a transistor, the voltage is about 0.2. I can then back into V5. I know the current is 424 milliamps, so that's this current right here, 424 milliamps. From I times R, I know this voltage, 20 ohms times 424 milliamps plus 0.2 gives you 8.69 volts. So those should be the answers for the H-bridge. On to problem number 2. This is a buck converter. If I have a 20 volt input and 90% duty cycle, find the voltages at V1 and V2. Now V1 is going to look like this. It's chattering on and off. The average voltage is the average of 20 volts when it's turned on. And when it's turned off, this is 0 volts, is actually minus 0.7. So it's 20 volts 90% of the time, minus 0.7 volts 10% of the time. DC voltage at V1 is 17.93 volts. That's a DC. And then by voltage division, the inductor, capacitor don't matter. DC, it's R over R plus 200 times V1 gives you 15.5 volts at V2. So there's the DC signals. For the AC signals, let's erase this. The AC voltage at V1 is roughly the peak-to-peak voltage. It goes from 20 down to minus 0.7, so this is roughly 20.7 volts peak-to-peak. Not exact. To get exact, you need to use Fourier transforms, which if you have MATLAB, you can do that. On tests, good enough to say about 20.7. To find V2, I've got to take the frequency of the input, find j omega L, put these in parallel, find, 1 over j omega C, minus 159 ohms. Put these in parallel, gives you 19 minus j 156 ohms. Take the inductor, j omega L, gives you this impedance. The voltage then is going to be what I'm measuring over the total impedance. That percentage of 20.7 volts peak to peak gives you 0.534 volts peak to peak. So that is the voltage at V2. For problem 3, this is a design problem. I want this to be 11 volts. Find the duty cycle and find C so that this is 250 volts or 250 millivolts peak to peak ripple. So here's your DC term, here's your AC term. At DC, if this is 11 volts, by voltage division I can find V1. V1 needs to be 12.64 volts. And then go backwards, I know the voltage, find the duty cycle. Turns out this needs to be 64% duty cycle. It's the voltage you want, plus 0.7 over the input voltage plus 0.7. This takes care of the 0.7 volt offset. So on a 64% duty cycle. To find C, one way to do that is assume C equals 0. Find the ripple at V2. I want the ripple to be 16 times smaller, so make that my output impedance divided by 16, 78 ohms. That's 1 over j omega c. I know omega, that's 754 radians per second. Solve for C. C is 2 microfarads. Problem 4, semiconductor relay. If I have a 17-degree firing angle, find the voltage at V1 and V2. Now at V1, what this is going to look like is if here's a sine wave coming in, I fire at 17 degrees. Let's change the color. So what's going to happen is at 17 degrees, I turn on, and I stay on till it goes 17 degrees past 180. Then I have the next waveform. I come up and follow it. Then it goes 17 degrees past 180. So there's your waveform. The average, this is the equation for the average from Bison Academy, is 10.77 volts on average. Once I know the DC voltage of V1, I can find the DC voltage of V2 using voltage division, 9.35 volts. The peak-to-peak voltage, roughly, is this distance. That's 1 plus sine of 17 degrees times 20 volts. That's about 25.8 volts peak-to-peak. Same trick. This is 754 radians per second. Find the impedance of the capacitor. Put these in parallel. Do voltage division. And you get 3.478 volts. Fourier transform. If I have 3 terms, I'll have 3 terms in the answer. The inductor is j omega L. Depends on frequency. If the frequency is DC, my load is 1314 ohms. If the frequency is 50 radians per second, I have j omega L plus R over the total times the input. Real part is cosine minus j sine, so there's my sine wave. And at 100 radians per second, if the input's a cosine, real part's cosine minus j sine, here's the input. So these are the 3 terms, DC, 50, 100 radians per second. And the last one, Boolean logic. To do NOR gates, you circle the zeros. So here's one group of zeros, there's another. This logic is A bar, B bar, C bar, or AC. I circle the zeros, so that's Y bar. Now use De Morgan's law. Negate both sides. Not Y gives you Y. Not A bar, B bar, C bar gives you A or B or C, and becomes or becomes and flip the signs. A and C becomes A bar or C bar. So to implement that, I have an OR gate, A or B or C, ANDed with A bar or C bar. Throw in double negatives to make those NOR gates. So that is quiz number 6 for ECE 320.